Supple, long-lasting, undamaged permed hair, the eternal desire of women everywhere. With conventional perming systems, however, there can be wide disparities in hold, with the perm quickly falling out or the hair badly damaged, making the dream of beautiful permed hair virtually impossible to achieve. Until now. Takara Belmont successfully created a long-lasting, low-damage, strong-wave perm through the development of Airwave. The principle of Airwave, in a few simple words, is to create the shape of the perm through cortex movement and fixing them by making CMC glass-like. The process may sound difficult, but in fact, this is the fundamental principle of a new perming system that anyone can use. Let's look at the mechanism we call hair then. Inside the stiff armour-like cuticle covering on a strand of hair is the hair shaft and cortex, which is a mass of cortex cells. These cortex cells are layered in rows inside the hair, joined together by a substance known as CMC. CMC consists of lipids and proteins and is stiff like glass. CMC proteins can be divided into water-repelling hydrophobic keratin proteins, which are SS-bonded, and hydrophilic proteins that combine well with water. The inside of a cortex cell also consists of keratin proteins, which are bonded together through SS bonding. In addition, both the CMC and cortex are affected very little by water. As a matter of fact, the cortex cells in particular normally repel water. When hair is wound around a roller, the top inner cortex layer is pulled side to side and the bottom cortex layer is pushed inside. Because both the CMC and cortex are stable, however, it is impossible to twist the hair no matter how hard you try. But the situation changes when reducing agents such as thioglycolate are brought into the picture. Entry to the perm, as we all know, begins with step 1, breaking SS bonding. The reducing agent dissolves the water-repelling hydrophobic keratin protein SS bondings, making the proteins hydrophilic, causing swelling to proceed. CMC changes dramatically from a stiff glass-like form to a rubber-like state. With this change in the CMC, the cortex cells also allow moisture and chemical agents to penetrate. The reducing agent penetrates the cortex and dissolves the SS bonding inside, and the cortex consequently swells. This phenomenon can only be initiated by a reducing agent. This progression of swelling from the CMC to the cortex causes internal stress, and this stress becomes the transfer energy of the cortex cells. At the point when swelling is completed, the hair is washed to remove the reducing agent so that no more SS bondings than necessary are dissolved. As the hair is washed, the hydrophilic proteins and keratin proteins in the CMC swell even more. The cortex cells push against each other, accumulating even more transfer energy. Because the CMC is in a rubber-like state, the cortex cells move towards positions where the stress is low. Here, moisture and suitable temperature are imperative. Airwave controls moisture and temperature, assisting in the transfer of cortex cells. With moisture and temperature optimized, CMC becomes even more pliant and rubbery. This facilitates the smooth transfer of the cortex cells, just as if they were drifting in water. The cortex cells transfer to their most comfortable position, where there is no stress on the hair wave. The hair is now in an unstressed state, with the cortex cells lying regularly in rows. This movement of the cortex cells is called creep. Airwave can effectively create this creep environment. Through the creep process, a foundation for waves has been created. The next step is to memorize this state. Memorizing process begins by first returning the CMC to its original glass-like state. This is done by removing excess moisture from the CMC while controlling the temperature with Airwave. The CMC then changes dramatically from a rubber-like state back into a glass-like state, and swelling of the cortex consequently subsides. The shape memory is the drying process that turns the CMC back into a glass-like state. By achieving this process without putting strain on the hair becomes wavy at a normal temperature and humidity. Finally, using an oxidizing agent, the keratin protein SS bondings are restored. The keratin proteins are returned to their original water-repelling hydrophobic state. The SS bonds inside the cortex cells are smoothly restored as the cells contract and the spaces between them shrink, returning them to their water-repelling hydrophobic state. The CMC and cortex cells are now fixed firmly in this position, a damage-free, stable perm in which the cortex cells lie regularly along the wave. In this way, it is possible to perm hair without causing stress by transferring the cortex cells and making CMC glass-like. This is the principle of Airwave. Conversely, from this perspective, the problem of conventional cold perms becomes very clear. That is, because they do not involve a drying process as Airwave does, and therefore do not make the cortex glass-like, the hair is stressed, and the waves are permanent pressed while the wet hair is still in a stressed, damaged state. Waves created while the wet hair is in a damaged state result in the phenomenon of hair going slack when the hair dries. In the case of hot perms, changes in the protein structure are brought about by the heat, which puts a tremendous strain on the hair. Moreover, because softening using the reducing agents takes some time, cases of impaired hair health have been observed. By using a slow creep time and ensuring the cortex is made thoroughly glass-like, Airwave minimizes damage and achieves strong wave strength, enabling long-lasting perms. Today, the conventional wisdom on perms has been transformed.